Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electric field, and so far electric field, electric potential related to that. So far we have covered concepts related to electric charge, Coulomb's law, theoretical and numericals, then electric field, basic concepts, both theoretical and numerical, and previously we covered the numerical problems series on electric potential energy. So in this video we are going to discuss about another important concept related to electric field, electric charge, electric potential, that thing, electrostatics, which is Gauss law. Okay, so before we discuss Gauss law, we have to discuss another important thing which is related to this, which is electric flux. So electric flux basically is the number of electric field lines passing through a surface placed along the electric field lines. So here the angle which the surface makes with the electric field lines, that plays a very crucial role. So the angle which the area vector, which is normal to the surface area, which makes with the electric field lines, that angle theta, that plays a crucial role. So this is the closed surface integral of the dot product of electric field vector and the area vector, or the surface area vector, which is perpendicular and drawn outwards, okay, normal to the surface, drawn outward. Okay, so this is electric flux. So what is the definition of electric flux? The number of electric field lines passing through the surface. So here, when theta will be 0 degree, theta will be 0 degree means the surface will be held upright, okay, like this. Okay, the surface will be like this, the electric field lines, and this will be the area vector. In that case, theta will be 0 degree, electric flux will be maximum, okay, because cos 0 degree, that is equal to 1. This is what? Equal to E ds cos theta. This is the dot product. So when theta will be 0 degree, in this position the electric flux will be maximum, and when the surface will be like this, the area vector and the electric field, they are at right angles with respect to each other, 90 degree, theta will be 90 degree. In that case, the electric flux will be equal to 0, because cos 90 degree is equal to 0. Cos 0 degree is equal to 1 maximum, and cos 90 degree is equal to 0. Simple dot product of electric field and surface area vector. So that is electric flux. So what Gauss law states is that it gives the relationship between the electric flux, that is the number of electric field lines passing through a closed surface, and the net charge which is enclosed or contained by that surface. So what the Gauss law statement, it states, is that the total electric flux passing through a closed surface area is equal to 1 by epsilon 0 times the net charge enclosed by the closed surface, where epsilon 0 is the absolute permittivity, or permittivity of free space or air. So simply Gauss law can be stated as this: the electric flux passing through a closed surface, that is equal to 1 by epsilon 0 times the net charge enclosed by that surface. So if we want to understand it, let's say we have a closed surface like this, any random closed surface, and here we have some charges, some charged particles. So we have positive charge plus q1, positive charge plus q2, negative charge minus q3. negative charge minus Q4, and again positive charge plus Q5, and negative charge minus Q6. So here if we apply Gauss law for the electric flux, which is closed surface integral of electric field vector and dot product with the surface area vector, that is equal to Q net by epsilon 0. So here this Q net, the net charge enclosed by this closed Gaussian surface, that is equal to plus Q1 plus Q2 minus Q3 minus Q4 plus Q5 minus Q6. This is the net charge. Okay, this is the net charge enclosed by the Gaussian surface. So the electric flux will be equal to Q1 plus Q2 minus Q3 minus Q4 plus Q5 minus Q6 by epsilon 0. Okay, when it is free space. Okay, absolute permittivity or permittivity of free space. This is the simple statement of Gauss law. It is applicable for any surface, any closed surface. So here comes the concept of what is a Gaussian surface. So basically this concept is a hypothetical one. It is a hypothetical closed surface area, closed surface which is chosen to determine the surface integral of electric field. And the most important application of Gauss law is to determine the electric field due to a charge or a charge configuration. So depending upon the charge configuration, an appropriate Gaussian surface is chosen so that Gauss law can be applied suitably and easily. Okay, so we can take any Gaussian surface. It can be a spherical one, it can be a cubical one, it can be a cylindrical one, any shape it can be taken to determine the electric field or the surface integral of the electric field. Okay, so here now we will discuss some other concepts related to proof of Gauss law, how Gauss law can be proven theoretically, and then we will try to derive Coulomb's law from Gauss law. Okay, so here we will try to prove the Gauss law by using a particular example, a situation. Let us say we have a positive charge plus Q, okay, and this is an imaginary spherical surface at the center of which we have a charge, positive charge plus Q. And let us say at a distance of r, which is the radius of this imaginary spherical surface, we locate a point P. Okay, this. Here we know that whenever we have a positive charge, okay, whenever we have a positive charge, the electric field lines always are directed away from it, okay, in straight lines. So here also the electric field lines at this particular point, if we take a small surface area, the electric field line will be directed radially outwards like this. Okay, this will be the electric field lines starting from this charge actually. Okay, so basically it will be starting from this particular point, from this charge itself, and it will be directed radially outwards, okay, at this point P. Okay, and also the area vector at this point P, okay, let's keep it here, this point P, and also the area vector, the small area ds, that area vector will also be directed outwards along the same line. They will be along the same line. Okay, so almost superimposed over each other, and the angle between them will be 0 degree. The angle between electric field vector, okay, the angle between electric field vector and the area vector, small area vector, that is 0 degree. Theta is equal to 0 degree. So this is here E vector and this is here ds vector. Okay, this. Now the electric field, the magnitude of the electric field at a distance r away from this positive charge at this point P, that is equal to, at point P, the electric field due to charge Q, that is equal to 1 by 4 pi epsilon 0 Q by r square. This is the electric field at point P. Okay, this. Now we know, according to Gauss law, according to Gauss law statement, electric flux phi E, which is, it is represented by phi subscript E, electric flux phi E, that is equal to the closed surface integral of the dot product of electric field and the area vector. Like this, we take very small areas everywhere. Okay, here we take a small area, then we take here a small area. Like that, we cover the whole surface by taking small areas and integrating them together, closed surface integral, combining them together. So here we have determined that the angle between E vector and ds vector, at all these places it will be 0, because if we take this place, here also the electric field vector, it will be like this, E vector, and the area vector also will be like this. Here also the angle will be 0, here also like this. This will be the electric field vector away from this electric field line, from this positive charge, and this will be the area vector. Here also theta will be 0 degree. For as many small areas we take, the angle between E vector and ds vector will always be 0. So here it will be, that will be equal to E ds cos 0 degree, the dot product of E vector and ds vector. That will be equal to closed surface integral E ds. Now here all these points that are located on this Gaussian surface, this closed surface is called as Gaussian surface. This is a spherical Gaussian surface. All these points that are located on this Gaussian surface, they are at a fixed distance r from this charge. Okay, they are at a fixed distance r from this charge. So as every other parameter is constant, epsilon 0 is constant, pi is constant, 4 is a numerical value, it is constant, the magnitude of charge is constant. So as r is constant, electric field EP at all points on the surface, the Gaussian surface, is constant. Electric field is constant. So as it is constant, it will be equal to E, or it will be appropriate to write EP here. Okay, EP closed surface integral of ds. Now the entire surface area of this sphere, that is equal to, the surface area of the sphere, that is equal to 4 pi r square. That is the surface area of this sphere, the curved surface area. So this will be equal to how much? EP into 4 pi r square. Okay, so here we have determined, as per this, the electric flux phi E is equal to EP into 4 pi r square. Okay, so this is one value, one equation, and this is one. This is equation 1, let's say, which gives us the value of the electric field at point P, and this is the expression of electric flux at that particular point P, the second equation. So here in equation 2, if we put the value of EP from equation 1, that is 1 by 4 pi epsilon 0 q by r square, what will happen? Let's see. So here if we put the value of EP here, phi E will be equal to 1 by 4 pi epsilon 0 q by r square, that is EP, into 4 pi r square. So 4 pi will get cancelled, r square will get cancelled, so we'll be left with q by epsilon 0, which is basically the statement of Gauss law. This is what Gauss law states, that the electric flux passing through any imaginary Gaussian surface, closed surface, is equal to 1 by epsilon 0 times the total charge enclosed by that surface. Here in this spherical Gaussian surface, the total charge enclosed is Q plus Q. There is only one charge. So here we have the electric flux is equal to Q by epsilon 0. Okay, this. So here we'll try to derive Coulomb's law from Gauss law. Okay, so we'll use the same diagram here, where we have a spherical Gaussian surface with a positive charge at the center, and here the electric field, and we have the small surface area at this point P. Okay, point P. Both E vector and ds vector are along the same line, directed in the same direction, so the angle between them is 0. So we know, according to Gauss law, electric flux phi E is the closed surface integral of the dot product of electric field vector and the surface area vector. If we take a small surface ds for this, so here as they are along the same line, so it becomes E ds cos 0 degree closed surface integral, and as the distance of this point from the charge is the same for all the other points on the spherical surface, they are at the same distance r, so electric field will also be constant, okay, because all the points on the spherical Gaussian surface will be at this, the radius distance apart. So this will be equal to E ds, and that will be equal to E into 4 pi r square. Now, according to Gauss law, electric flux phi E is equal to Q by epsilon 0. Epsilon 0 is absolute permittivity or permittivity of free space. So from this equation 1 and this equation 2, we get that E into 4 pi r square is equal to Q by epsilon 0, this Q. So that implies electric field at point P, that is equal to 1 by 4 pi epsilon 0 Q by r square, which is the expression of electric field. We know this. Now let us say we have a positive test charge Q0 placed at point P. So the Coulombic force repulsion, because both of them are positive, the Coulombic force exerted on this charge Q0, that is equal to Q0 into E, because we know electric field is the force acting per unit test charge. Electric field is equal to the Coulombic force acting per unit test charge in an electric field. So Q0E, so that implies that is equal to 1 by 4 pi epsilon 0 q0 q by r square, which is the expression of force given by Coulomb's law. So here, using Gauss law, we have derived Coulomb's law. Okay, Coulomb's law using Gauss law. Okay, so this is the thing. So here we have discussed about Gauss law and all the other related things, that is how to derive Coulomb's law from Gauss law and how to experiment, theoretically, mathematically prove the statement of Gauss law. So this is, always remember, this is the general statement of Gauss law. So if we have any random shape Gaussian surface, you can take any shape, and we have a number of charges, we have to take into consideration their sign. The electric flux phi E, which is the closed surface integral of the electric field, and the area vector, the dot product of these two, that is equal to 1 by epsilon 0 times the net charge enclosed by that surface. Net charge is the total net charge taking into consideration their sign, whether they are positive or negative. So here we have discussed about Gauss law. Okay.